Oh.
So.
Yeah, I was gonna say, I got
Sorry.
an iPhone last year.
Sorry.
I never used it.
Yeah, me too. Okay, I'm alone.
5-3. Okay, the two things we've done, well actually three things. We've turned an X value into a Z-score. We did that 2 days ago. I'm just going to give you that formula so you've got it. We take the X value, you subtract the mean, and you divide by the standard deviation. Then yesterday we learned two functions on the calculator. The NCDF of the left Z-score to the right Z-score. What does this answer that it gives us, what does that represent? The NCDF value.
Area.
It's the area under the curve, or the probability then. So this gives us the area slash probability. They're the same thing. And then the other function we used on the calculator was that INVNorm. What did we feed INVNorm?
We said in the norm, find
Area.
It finds these scores, but what do we got to feed it? Which area?
To the left of.
Left area. We'll call it just left area. Left area. And it gives us back a Z-score. All right, those are the three things we've done. Now we're going to do some examples where it all incorporates together.
Is that Z minus score?
Nope,
Or
Z-score.
Okay.
All right, so our first example.
Question on
yes.
review
Thank God.
tomorrow that you put on Friday.
Correct.
Can I get some review?
Yep, I don't have it copied yet, but
Can you
After
get
next
that
hour.
by the end of the hour?
by the end of fourth hour.
Next hour.
Oh, we'll see.
I won't remember.
All right. This particular car's mileage is normally distributed
especially if you're wearing like
with a mean mileage of 28 miles per gallon and standard deviation of 1.6 miles per gallon. If I randomly select a car I'll just do one part here. Can you find the probability that this car has a mileage greater than 31 miles per gallon? Yep, now I'll wait.
What does the disk mean here?
What does what mean?
The disk?
Normally distributed. I mean, if it's that bell curve, that nice smooth bell curve. So whatever car this is, a Ford Fusion. If they do all the Ford Fusions, what it's saying is if I tested all the Ford Fusions for miles per gallon, they're saying that the average is 28 miles, because not every single car gets the exact same thing. But the average for this big whole sample of all the Fusions is 28 miles per gallon, and here's the standard deviation, 1.6. So they're all kind of close together. Now I'm asking, if I randomly select another Ford Fusion, what's the probability that the one car that I select has this particular miles per gallon? Are you ready? So here it is. Normally distributed. The average is 28. I am looking for the probability that the car I pick has a mileage over 31. Well, 31 somewhere over here. I don't even know. Let's just say that's 31. I'm looking for the probability, which is area, that it's over 31. So to answer the probability question, I've got to find this area. What on the calculator gives me this area? NCDF. What do I have to feed NCDF?
2831.
I need to feed it z-scores. Do I have z-scores yet? No. How do I get z-scores? With this formula. 31 is not a z-score. Remember, z-score is how many standard deviations above the mean. Am I 31 standard deviations above the mean?
No.
No. The standard deviation is 1.6. I don't quite know, but we're going to figure it out. So we need to first turn 31 into a z-score. So the z-score for 31 is 31 minus, what is the mean of this distribution?
28.
28. Divide by the standard deviation,
1.6.
1.6. And we're going to give z-scores out 2 places. 2 decimal places out for z-scores. How many standard deviations above the mean is this?
1.88.
1.9.
2 places out.
Just kidding. 1.8.
1.88. So the z-score for 31 is 1.88. What's the other z-score I'm going to use? What's my other edge of my shaded region?
Oh, 10 to 10.
10 to the 10th. So now to get the area or the probability, you're going to use NCDF, left z-score to right z-score. So 1.88, 10 to the 10th. So what's the probability that the car I pick gets that gas mileage?
Not high.
Probably not very high. Anybody?
0.0301.
Sounds about right.
Did I do it right?
3% of the graph? I'm going to say yes. Let me see, what do I have? Yes. Any questions on what we did there? I think the picture of what you're trying to find tells you exactly what to do. I draw pictures all the time.
Pictures just for the actually help.
Okay.
Otherwise they have to say we just.
Okay.
Yeah.
Tedious. Okay, number 2. Same idea, then I'm going to switch it up after number 2. So this one, I just want you to get good at it so you can see what's going on. Okay, time spent in a supermarket. I'll just say the store. Is normally distributed. And the average time with the mean of 45 minutes and standard deviation 12 minutes. You're going to randomly select one person. Can you tell me the probability that that person spends between let's go 30 and 60 minutes in the store? So I'm looking for a probability, so I know that that goes to the area on the curve. So I'm going to sketch it so I know what area I'm trying to find. So this is all people that go to this particular store. All of the time spent in there is normally distributed, where most people are spending around this 45-minute mark. And I'm looking to see what's the probability that I pick someone who spends between 30 and 60. 30 and 60 in this big part of the graph. So, in order to find that area, I'm going to use NCDF. But what do I got to feed NCDF? Z-scores, not the original X values. So you got to convert both 30 and 60 into a Z-score. So let's do the Z-score for 30. So it's 30 minus the mean of 45 divided by 12. And we go out 2 places on Z-scores.
Negative 1.25.
Negative 1.25. And then the Z-score for 60.
I got your short.
All right.
It's positive 1.25.
Oh, I'm symmetrical. Oh, yeah, I could have got that. 1.25. They're not always symmetrical like that, but I did pick one that is. So it's going from negative 1.25 to positive 1.25. And now it's just button pushing.
I feel like this place it says 6%.
No, because that's exactly 1 and exactly 2. These are,
38%.
it was 34%, that's 1. So it's going to be more than 68, but less than 95. Closer to the 68 than the 95.
78.87.
0.78.
Good, I guess, and hold that.
7?
87.
87. 887? 7887.
Jeez.
I'm going with that. All right. Yep. A little bit of work. Now these next ones, I'm going to change it up a bit. But those are not difficult. Do you agree? If it's asking for a probability, you use your NCDF. You just have to convert your data values into Z-scores. Okay, number 3.
How many are we doing?
Cholesterol levels
So you're being serious again?
of American men.
Yeah, you're being serious? Yeah. 4? Thank you. 5.
Oh, 5. Alright, that's pushing.
Are normally distributed.
Does it always have to be normally
Yes,
distributed
this
or for
only works with normally distributed data. Otherwise, forget it.
What does?
This stuff we're doing. The data has to be normally distributed to do these probability questions.
So if the problem doesn't say it's normally distributed, is that?
You can't do it.
They,
What does that mean, normally distributed?
It when you do the data, it all fits into this graph. I was to make a distribution for it. You have all those big tall bars in the middle, and then they get thinner as you go out. It has that nice symmetrical shape. And to be that, your mean, median, and mode are all approximately the same. All right, with an average or a mean, I don't know what they actually measure this in, of 215. I don't know what the units are. I didn't write them down.
I feel like that's high.
And standard deviation of 25. Okay, we're gonna look at a sample of 600 men. My question is, how many will have a level less than 170? Okay. Why is this question different than the other 2 that I asked you? Yeah, because my other 2 asked for, what's the probability that this one thing I pick is in this range? Now I'm asking for, how many out of the 600 would I expect to have this level?
Is it input norm?
It would not be.
I know what it is, Schwartz.
What is it?
PDF.
No, it is not. We haven't touched NPDF and we're never going to.
It was a good guess.
Okay, I'm going to show you the graph. Okay, with the average of 215, So if I had this thing to scale, and I had, I don't know, 600 ping pong balls to represent the men, and I had this big rope up here that was shaped like this. If I dropped those 600 ping pong balls in there, they would all be dispersed evenly through here, where each ping pong ball represents one of the guys. My question is, how many would be less than 170? I'm looking for how many of the ping pong balls would be back here. How do you think I can turn this area into how many? Yeah, we're going to find the percentage here and then multiply by 600. So it's just an extra step beyond what we did in the first two. So if this was 25% of the graph, I would expect 25% of these men. If I had said what percent have or how many would have a score less than 215, you'd tell me 300, because there's 300 on this side and there's 300 on this side. So what I need to know is this area, and then I'll multiply. So it's one extra step to get to how many. So we got our negative 10 to the 10th z-score. I just need the z-score for 170.
I got you.
All right, 170 minus the 215 over the 25. Go out 2 places if you can. Negative 1.8.
Every time that, Casey, every time.
Okay, so now that we've got the z-score, we want to get the area. And the left edge is negative 10 to the 10th. The right edge is negative 1.8. How much of the graph is shaded?
0.035.
0.0359. So far, so good? So I would expect 3% of my sample to be down here. So to figure that out, 600 times 0.0359 is about how many men, approximately?
22.
22.
It would be 21.5, but
Okay.
barely have half a man.
They do that, though. They'll say approximately 21 and a half. Statistics always gives parts of people, parts of kids.
Like a half your heart.
Yeah. So I don't care if you want to. If it makes you feel better to make them whole people, go ahead. All right.
Makes you feel more humane.
Yeah.
Whatever floats our boat for us.
Yep. I care about all this work, this process. That's what I care about.
We have 2 more examples for it?
I think so.
Let's only do one.
Each one's different, though. Now I'm not repeating myself.
Okay, how long is it?
Both the same as that one.
Oh, that's not bad.
Okay, number 4. Let's see, the length of time
Length of time. That's the next.
worked at a particular company.
Oh.
By all of its employees is normally distributed. With a mean time of 11.2 years.
Pretty good company.
And standard deviation 2.1 years. Okay, due to cutbacks, you have to lay off the bottom 10% of your employees. Lay off the bottom 10% in seniority. So what I'm going to ask you to find is, what's that cutoff? How long could someone have worked there and get laid off? So find how many years worked and get laid off. So once you get that written down, I always like to make the graph on these because it just kind of gives you a picture. Yeah, how many years would you have worked there and still get laid off? So the bottom 10%, how many years would that person have worked? So the longest that they could have worked and still get laid off. $2.8? Wrong.
Yeah, just guess.
Yeah,
Oh, I
not
thought you,
even
like,
close.
figured it out. I was like,
He's not even
whoa.
close. All right, you ready?
7.8.
Okay, here we go. Here's the length of time worked by my employees. I don't know how many there are, but they're all ping pong balls in here. Here's the average, 11.2. Okay, it says you're going to lay off the bottom 10%. What is that giving me according to my as part of my graph?
A Z-score.
It's the area. Dang.
Try again.
Good try. So it's the bottom 10%. Where are those people at? Down here, the left-hand tail. I know that this area is 0.10 because of 10%. Percent to a decimal, kick it over. Got it?
No, I knew that.
Okay. So what I'm trying to find is how many years is this? What cuts off the bottom 10% from this upper 90%? Not that I need the 90. That's the goal. Find that X value.
I bet you're working backwards in
Okay.
the equation. I bet you.
No.
Okay. Never mind. Take it back.
So this is different. This time I know the area and I'm trying to find an X value. Well, I don't have a function that gives me an X value, but I have a calculator function that gives me what? It will give me the Z-score for this spot. So I can find the Z-score for this spot with INV-norm, and then I'll turn that Z-score back into an X value.
That's a lot.
It's 2 steps. So to figure out this Z-score, we're going to use,
What is that 0.90?
that's how much area is to the right. 10% behind me, 90%. We're going to keep the top 90%. Oh no, it's the whole,
Here.
that's all 90% of the graph. Keeping the top 90% in seniority, getting rid of the bottom 10%. Okay, so to turn this area into a Z-score here, we're going to do INV-norm. What do you have to feed INV-norm again? Which area? To the left of the what I want. So if I'm standing here, how much area is to my left?
None.
0.1. Give me this Z-score to 2 places out. How many standard deviations below the mean is this person?
-1.28.
Negative 1.28. So if I know the Z-score, I can use that little plug and tug formula to get it back to what data value has that Z-score by using this formula. I know the Z-score, I know the mean, I know the standard deviation, I'm trying to find the X. So the Z-score we just calculated was negative 1.28. Don't know the X value. I know the mean is 11.2 and the standard deviation is 2.1. So do the 2 algebra steps on your calculator. What are the 2 algebra steps? Multiply by 2.1, then add 11.2. Can you see that in your head without me writing it down? So what is the X value going to turn out if you multiply by 2.1, add 11.2?
8.532.
Approximately 8.5 years of service, and you're going to get laid off.
Holy crap.
Hey, I said 7.8.
Yeah, you did.
I said 2.
Yeah, you did.
8.5 years and you still get laid off.
Mm-hmm.
I did not get that. I got like.
You want me to check? Oh, my TV's not on.
I did.
Should be negative 1.28 times 2.1.
And that is negative 2.688.
and just take that number plus 11.2.
Looks like you're on the phone. Oh, oh, it wasn't, okay, I get what I did.
Okay,
Thank you.
all right. It's always good to check to make sure you can run the calculator right. Okay, last one. Yay.
As long as that one.
Approximately.
Just gonna put a page.
Oh, that was a bad one.
Okay. When you're in college, and if you decide to go on to graduate school, just like when you get from high school to college, you have to take the ACT.
I don't want to come to school
Okay.
tomorrow.
When you go on to grad school, you'll probably have to take one of two different tests. You know how for college entrance we have ACT and then there's SAT? But we don't do much with the SAT, but now we're going to be doing SAT. There's two graduate school tests. The GRE, the Graduate Record Exam. The average score on this thing is 1,500 with a standard deviation of 300 points. The other graduate school test you can take is called the Miller Analogy Test, MAT. This one has an average score of 50 with a standard deviation of 5 points.
Matt and Greg.
Okay, so you as a future graduate student don't know which school you're going to go to, so you take both of these. Your scores.
I would die.
Yeah.
No, thank you.
You got on the GRE, you got a 1775.
But I feel hard.
And the MAT,
Just bombed.
you got a
42.
56.
Good for you.
Which one did you score better on?
The SAT.
How do you know?
How do I know?
What can, and the scores are normally distributed.
Because if you add 300 to 1,500, that's like 1,800, and you add 5,
Yeah, that's
50,
less.
55. And you're less than the GRE, but you're more than the MAT.
She's got the right idea. She didn't tell you what I think you need to know.
Add the 300, you get.
What are you? Why are you adding 300 to it?
That's one standard deviation.
That's one
away.
standard deviation above the mean.
And then your GRE score is still below one standard deviation. But if you add the 5 to the mean on the MAT, you're above one standard deviation away.
So what they're telling you to do is find the Z-score for each of these and see which one is farther above its mean.
How do we know?
Do we actually have to do the math for it?
Same thing.
Right, I gave you the standard. These are standard deviations. This is a symbol for standard deviation.
Yeah, I know.
Oh, 1,500. Let's turn 1775 into a Z-score.
So it's a different test.
You know,
Yeah, that's why. You're on the standard deviation.
with tabs on that one.
So we did better on the math?
I think we did better on the math.
So we just used our inference skills to figure
Yeah, you could estimate this one and get it because of that 5 being easy, well, and the 300 being easy too. So how far above the mean were we on the GRE? What is the 1775 minus the 1,500? Oops.
I got .91.
About 9.2, not quite one standard deviation above the mean. So we were about here. The other one, also normally distributed, 50 is the average. You got a 56. So 56 minus 50 divided by that is 1 point something, 1.2. So which one are you farther up on the normal curve? The MAT. So you have to compare Z-scores there to tell. You got to compare apples with apples, Z-scores with Z-scores. Okay, your assignment today then. Yep, I'm going to find the assignment. What's today? Wednesday. Page 217. 1 through 15 odd. And we're going to skip 7 and 13. Because each one of them have parts. So that might seem like I took a lot off there, but there's like A through C on these.
Thanks for telling us.
Yeah. Didn't want you to think I was being really nice today or something.
Thank you.
That never happened.
No.